what I'd like to start looking at are some notes of complex numbers. And, I know we've studied complex numbers, in other math classes, talked a little bit about in this class as well, but we're also going to start looking at complex numbers through the lens of a polar graphing system. And so the first thing I want to do is just kind of, reiterate or remind ourselves about graphing complex numbers. There's always a real component and an imaginary component. And so as we kind of look through the notes here, pick a nice red here. So the first component is always the real. The second component with the I would be the imaginary. And the way I would say, okay, plot this is almost thinking about it on an XY axis. I'm going to go 2 root 3 in the real direction, so however much that is, and going up 2 in the imaginary direction. So if I think about okay, this is the real direction, this is the imaginary direction, bam, there's my point. And this distance here, I could think about as 2 root 3. This distance here, I could think about it as a distance of 2. But remember that 2 is in the imaginary direction. So it's like I would associate an I with that particular point. But I do know that 2 root 3 in the real, 2 in the I, there would be my point, 2 root 3 plus 2I. Now, the distance that is from the origin, we're going to call that the magnitude. And I picked a nice complex number because I could easily find this distance by doing the Pythagorean theorem. Or if I don't recognize the Pythagorean theorem, because that's a right angle there, if I don't recognize this, I'm using the Pythagorean theorem, but I might also be able to see that, wait a minute, this has a distance of 2. This is a distance of 2 root 3. This is our old friend, our 30, 60, 90 triangle. So that angle right there is 30 degrees. So if that's the case, and that's 2, that's in the x position. So I know that its magnitude is 4. I could have easily gotten that by saying, okay, that's 12 plus 4 is equal to m squared. Or 16 is equal to m squared, so m is 4. And I know I'd be introducing a square root, so I would thinking of as a plus or minus here, but magnitude is always going to be a distance. So there's not going to be any, there's no displacement or direction to this. It's just a distance, so it'd always be positive. Now, if I want to also talk about that argument of that, or how many degrees is that magnitude or that segment rotated from the positive real x-axis, I've already mentioned that that's 30 degrees. And so again, thinking about, the angle that's formed right here, this angle right there, that angle's 30 degrees. And so I would talk about that as the argument of that particular, complex number. So this complex number, 2 root 3 plus 2I, could also be represented if I wanted to think about, okay, what else do I know about it? I know it has a magnitude of 4, and it has 30 degrees as its angle that's from the positive x. But we have to somehow distinguish that this is not a polar representation of a point. This is not the polar plane. This is something that's still in the complex plane. There's the real number system and the imaginary number system. But the key pieces are this 4 and the 30. Okay, so what we're going to think about, what we're going to do is introduce this polar form, which has, you can kind of see it, a little bit of a preview down here with this r cis theta here. We're going to write that in r cis theta, and you pronounce it like that, r cis theta, but I'll explain kind of what that means, as we go through this next example. But this is the polar form. It's focusing on the magnitude and the angle that's created with the x-axis. So I think about it's 2 root 3 plus 2I. So we just said that was 4, and then this idea of cis, 4 cis 30 degrees. Where does that come from? Well, it's 4 cosine of 30 degrees plus 4I sine of 30 degrees. And again, if we think about, okay, where is this abbreviation CIS coming from, this cis? Well, the C comes from cosine, The I is the imaginary component, and the S is the sine. So if you were to expand this and think of, okay, what is exactly like 30 degrees? What is the cosine of 30 degrees? Right? What cosine of 30 degrees? So there's your root 3, 2, and 1. So you'd say, oh, that's 4 times root 3 over 2 plus 4I times 1/2. So that's 4 root 3 over 2, which is 2 root 3 plus 2I. So it just basically is the formula that gets you back to that particular complex number. And again, we think about like the cosine function is associated with the x, and so that's in the x direction. And then the sine function is like in the y direction, the imaginary is this direction right here. But really, all that's important, because it's always going to be cosine, it's always going to be sine, is how far is this distance, that magnitude of 4, and that's what we see right here is the 4 and the 4. And then what is the angle, right? What is this angle right here? It's 30 degrees. And that's exactly what the angle is, or the argument there. So instead of always writing 4 cosine 30 degrees plus 4I sine of 30 degrees, we just kind of abbreviate it by saying, okay, what's important? 4, right? That's the magnitude. And then the order is always the cosine, and then the imaginary component, which comes with sine, and then the 30 degrees. So this is sort of the condensed, abbreviated polar form of the complex number 2 root 3 plus 2I. Now, so if I see that, if it says, oh, look at, write the complex number 4 minus 4 root 3I in r cis theta form, which is, like I said, is the polar form. So one thing you can do is graph this point as if it were like, just on the x-axis being the real and the y-axis being the imaginary. So if you were to graph over 4 and down, so I go over 4 to the right and down 4 root 3. And I think about, okay, how far is this from the origin? Okay, well, that's 8, because it's a nice angle, right? How nice is it? That's 60 degrees. I still want to think about that argument. I mean, I suppose you could think of it as like a negative 60, but I want to think of it as a positive angle. So now that's a 300-degree angle. So the things that are important here are the magnitude of 8 and then the angle of 60 degrees, or sorry, 300 degrees, because that's the reference angle of 60 in quadrant 4. So how would I write that? I'd say 8 cis 300 degrees, and that's it. I already know what this means. I know that in an expanded form, I would have said, oh, that's 8 cosine of 300 degrees plus 8I sine of 300 degrees. And I don't have to write this, but then I could say, oh, what's the cosine of 300 degrees? Well, that's 1/2. So then I'd have 8 times 1/2 plus 8I in the sine of 300, which was negative root 3 over 2. So I'm just checking my work here, but yeah, that's exactly the imaginary number that I started with. So this is like the rectangular form, or a plus bi form, and then if I want to put in r cis theta form, which is right here, so this is what we call as the polar form. It represents the magnitude and the angle that it creates. And if you think about why are we calling it polar form, because those are the two pieces in polar graphing that are important, an r and a theta. So we're just kind of just examining the complex plane through the lens of basically polar coordinates. Okay, so I'm going to work out examples 6 and 7. Feel free to follow along, or, actually I'll do 8 as well, and 9. Ooh, they just keep coming. And 10, how exciting. But feel free to pause the video, work out the solutions, and then see how you did. If you need a little bit, like I said, need more guidance, then, just continue watching as we go. And I hope, we'll just go from there. So negative 9 plus 9I. So again, my thought would be, let's think about what does this look like just on the XY axes, or the real and imaginary. So going left 9 and up 9I. So going left 9 and up 9I. And again, if I were to label this triangle, I'd probably label it like this. And notice I did not really put an I here because I know it's in the I direction. But then, like when I go ahead and draw my hypotenuse here, I know it's the right angle. Oh, it's a 45, 45, 90 triangle. So the reference angle is 135 degrees, x root 2. Things that are important will be the hypotenuse, which is 9 root 2, cis, and then 135 degrees. So there, again, I could just leave it like this. There's a representation of the polar form of -9 plus 9i. Okay. Now 3 plus 4i, write that into r cis theta. Same thing. You maybe draw out your particular complex number. So I'm going to go over 3 in the real and up 4 in the imaginary. So there's 3. There's 4, make my hypotenuse. Well, this is our good old friend, right? A 3, 4, 5 triangle. So at least I know what that magnitude is. And then the question is, what is that angle, that theta? It's not 30, 45, 60, 90, or anything that's like a nice value. So what I might have to do is represent that theta as, an inverse trig function. Everything's defined in quadrant 1. So I could say, oh, that's inverse tangent of 4/3. This would be one example. So when I'm writing this complex number, I could say, okay, that's 5 cis, and then my angle would be inverse tangent of 4/3. So it may not look the cleanest, it might not look aesthetically pleasing as the other angles, but if your argument, which is this angle here, isn't necessarily of a quote-unquote nice value, then you're sort of stuck. Okay, now, 8 cis 2 10. Let's write that in a plus bi form. So a couple ways we can think about this. One, you could draw it, and I love drawing these things out. 8 with an angle of 210 degrees. So you go 210 degrees, that's a 30-degree reference angle into quadrant 3. That's a hypotenuse of 8. And if this is a 30-degree reference angle, right here, that's 30 degrees. So that would mean that that I could complete this triangle by making this a -4 and making this a -4 root 3. That would satisfy our 30, 60, 90 triangle. And then I can translate, a plus bi form, well, this is the real direction, and then this is the imaginary direction. So that would be -4 root 3. Complete that 3, minus 4i. And that would be the complex form, a plus bi, of that particular polar graph or polar point. Now, let's say you didn't want to just necessarily graph this out. You could also have simply, erase here. You could also have just expanded this 8 cis 2 10. You could actually have just done what it says do 8 cosine. Oops, go to pen here. 8 cosine of 210 degrees plus 8i sine of 210 degrees. And if you drew your 210-degree reference angle, if this is the way you wanted to do that, that's 30 degrees. So that's -1, that's 2, that's root 3. So the cosine negative is negative root 3 over 2. So it's 8 times negative root 3 over 2 plus 8i, and then the sine of 210, which is -1/2. So now we get -8 root 3 over 2 minus 8i over 2, which is equal to -4 root 3 minus 4i. So again, another way that we can come up with the exact same number. I don't care how you solve these. I like to see, me personally, I just like to do that because to me that's less work than having to expand and then rewrite the triangle anyway in case I forgot what 210 was. So, but it's up to you. Okay. And then same thing, 2 cis 60, whichever way you want to do it. I might just continue with my particular method of drawing a graph. So I go back to maybe my pen here, select that. And I'd say, okay, 2 and a 60-degree angle. So I draw, here we go, 60 degrees. 60 degrees, right here's my reference angle with a radius of 2. So if that's 60 degrees, right here, 60 degrees, that means opposite 60 is in the root 3, and the hypotenuse is 1. So this is 1, and this distance is root 3. Because that's in the imaginary direction, I would say that's 1 plus root 3I. So there's the a plus bi form of 2 cis 60. Now, multiplying these out. So here's the thing, like I can multiply this out, like, and I could just follow along and say, oh, okay, negative 4 root 3 times 1, that's negative 4 root 3. Negative 4 root 3 times root 3 would be negative 12i. Negative 4i times 1 is negative 4i, and then negative 4 times 3 is negative 4 root 3, but then you have an I squared. And remember, I squared is negative 1. So this becomes negative 4 root 3. This becomes negative 16i. This actually becomes positive 4 root 3 because the I squared became a negative to cancel. And so like that cancels with that. And so I get negative 16i. So I know this is negative 16i, and this is really kind of like the algebra 2 way to solve this problem. So why, you might wonder, why are we having this as example 10? Well, let's look at their polar representations first. Let's look at this polar representation over here. And let's see, negative 4 root 3 minus 4i. So that actually looks really familiar. I think we did this. Negative 4 root 3 minus 4i. Oh, we got close. Number 5 was close to it. So that's okay. So we will just redo that. Negative 4 root 3 minus 4. Oh, actually, we did do this. Isn't this the 8, 2, 10? 8 cis 2, 10. Haha. So I knew there was some method to my madness. I have it right here. I just haven't simplified it. So if I were to draw that out, look at that. See how exciting this notes is, even on an e-learning day. So I go over negative 4 root 3 and down 4. Over negative 4 root 3, down 4. So negative 4 root 3 down 4. Just again, visualize that's a magnitude of 8. So I'm 8 units away, and that's cis, an angle of 210 degrees. So that first point is 8 cis 210 degrees. Now, let's take a look at that second point. This one right here, 1 plus root 3i, which I know I just did. And just to kind of visually see that this is 1 and this is root 3 in that direction. So I knew that that was 2 with an angle of 60 degrees. So that's 2 cis 60 degrees. So here's the polar representation of the second point, and then here's the polar representation of the first point. And when I multiply those two together, I know the product should be negative 16i. And I'm a little suspicious because when I look at these two numbers here, I see an 8 and a 2, and I know their product is positive 16, not negative 16. But what if I somehow take this 8 and take this 2 and thinking about, okay, well, that is 16, and like, and if I start to look at my angles, 210 and 60, well, 210 and 60, if I were to put them together to think about them in a way that I could represent this negative I, think about negative I. Negative I is straight down here, like in the I direction, right? The imaginary direction is vertical, and negative I straight down, that's an angle of 270 degrees. And look at, I have a 60 and a 210. If I add them together, that could give me 270 degrees. And that's my whole point. I hope you see that. That's the whole point, is that if you have two points that you want to multiply and you have them represented in an a plus bi form, you could convert them to their polar representations, simply multiply. If I go here, simply multiply the arguments, the magnitude, so 8 times 2, which gives you 16, and then add up your arguments, add up the angles. 210 plus 60 is 270. So then how do I make sure I have the right representation of this? So then I'd say, okay, this is equal to, if I drew that out, I'd go 270 degrees, I go straight down 16 units, that's in the I direction, so that's equal to negative 16I. Okay, so that's a lot of me talking, and maybe that this is making sense. If not, go back, rewind. I'm actually going to break this down into a second video, a little bit shorter, that'll work out the next couple of examples and talk about this theorem right here. So if things made sense, great. Go ahead and start the next video. Otherwise, maybe rewind this, take a look at maybe a few more, just going through those one more time, and then, check out the next video. Okay, so